تسمعوني كويس والسكرين شيرنج كويس برضو؟
تمام يا محمد، الصوت والصورة واضحين.
ممتاز. اوكي. مرحبا بكم جميعا. السيشن بتاعتنا 7th session today we are going to dive deep في algorithm اللي هو مهم كتير جدا. هو حيبني على ال knowledge اللي عملناها through the previous sessions. we will be building up with our first algorithm. أول algorithm اللي عنده real world application و real world impact و especially real world advantage compared to classical approaches. فالجروفر search algorithm هو algorithm that executes a certain task of search في space معين. And from what we are going to see في السيشن بتاعتنا, it will be beneficial to opt to use the Grover search algorithm في عديد التاسكس بتاع السيرش واللي يعطي advantage على classical approaches. قبل ما نفسر الالجوريزم بتاعنا, هنبدا بسيمبل جيم اللي حتعطينا intuition و understanding الستبس بتاع الجروفر سيرش algorithm afterwards. So هنبدا بجيم simple جدا. We are going to start with a list with n elements on a list, initial list n elements, وكل element فيهم حيبتدي بالفاليو 1. So الليست بتاعتنا حتبتدي ب equal elements. Each of the n elements will be having the value 1. وفي elements في الليست بتاعتنا اللي هم marked, اللي هم important and searched في الليست بتاعتنا. والجيم بتاعنا الجيم بتاعتنا حتكون الايفولوشن بتاعها كما يلي. حتكون في iterations, وكل iteration حتكون متكونه من 2 phases. First phase اللي هي الquery, where كل marked element هناخد الفاليو contained في الماركت element ده وهنعمله له الفليب بتاع الساين بتاعه. يعني اذا كان هو كان بوزيتيف فاليو هتكون نيجاتيف, هتصبح نيجاتيف فاليو والعكس بالعكس. والiteration الثانيه اللي هي الانفرجن, من الفاليوز of each and every element marked or unmarked في الليست بتاعتنا will be reflected over the mean of all values, the average بتاع الفاليوز بتاعتنا في الليست اللي هنعملها في الجيم بتاعتنا. For example, هنبتدي باكزامبل معين where we have 8 elements في الليست بتاعنا, وعندنا the fourth element, element رقم 4 هيكون الماركت element. هنبتدي بvisualization with a certain plot للليست بتاعنا من first element لل 8th element. This is the initial stage or the initial step. من كل element في الليست كده هتكون في value of 1 as an initial value. هتكون في application كما قلنا بتاع iterations, consecutive iterations, وكل iteration هتكون فيها query وinversion زي ما قلنا. في الفيرست كويري هتكون في انفرجن للساين بتاع المارك element واللي هو الاليمنت نمبر 4. يعني هو كان في الفاليو 1 هيكون في الفاليو -1. بعد الكويري هنعمل انفرجن, وعشان نعمل انفرجن لازم قبل كده نحسب المين اوف اول فاليوز ولا الافريج بتاع الليست اللي هنشتغل عليها. والافريج هنا هيكون 0.75 because it is 1 مع 1 مع 1 مع 1 7 مرات مع إلا 1 للماركت element. So it will be over 8, so it will be 0.75. بعدين هنعمل inversion على اللاين المحدد هذا. اللاين هذا اللي هو يمثل the mean of all values. So for the values above the line هذا هتكون في inversion اللي هي really asymmetry alongside this line. So the values which were 1 will become 0.5. So the 1 will be subjected, هيكون في inversion للvalues 1 to 0.5 alongside this particular line. For the marked element of our list هتكون في also inversion alongside this line, بس هتكون في inversion up الفاليو contained في الماركت element يصير لها increase، حتكبر، حتكون يعني 2.5 زي ما بنشوف هنا. So the unmarked elements حيصبحوا 0.5 for the marked element حيصبح 2.5. واللي نلاحظه من الفيرست iteration هنا انه الماركت element الفاليو contained في الماركت element حتكون في increase من 1.0 to 2.5. for the unmarked elements حيكون في decrease من 1.0 ل 0.5. the first iteration بتاع الجيم هنا allowed for an increase for the special for the value contained in the special element of our list. وفي الاليمنتس اللي هم not special ولا unmarked elements حيكون في decrease. هنعمل iteration مرة أخرى the second iteration right here and from 2.5 it will become minus 2.5 عشان الانفرجن بتاع الساين. مرة أخرى we calculate the mean of all values right here, it will be this line, and then بنعمل inversion مرة أخرى. واللي نلاحظه هو نفسه الامبليتيود contained in the marked element element اللي هو special اللي هو searched for حتكون في increase from 2.5 to 2.8 something like that. For the unmarked elements حيكون في decrease from 0.5 to 0.25 something like that, 0.3. We are dealing here with absolute values, so يعني here we don't care about the sign, we care about only the absolute value بتاع الفاليوز في الليست بتاعتنا. ونفس حاجه نلاحظوا انه الامبليتيودز ولا الفاليوز contained in the marked element they increased، بس الفاليوز contained in the unmarked elements they decreased. Let's apply once more الالجوريزم بتاعنا ونعمله بالطبيعه الكويري والانفرجن، ونلاحظ انه نفس الاوتكم لهنا persisted، لكن الديفرنس between الماركed and unmarked values نقص، لهنا difference between the marked element values and the unmarked element values is clear. يعني difference is very very large. لهنا but لهنا في ما بين الماركed and unmarked elements there is a difference. The unmarked elements have a less value compared to the marked element، ولكن the difference is less obvious بعد a third iteration. And إذا كان نعمله fourth iteration so the results are completely different, totally different. So نقدر يعني بعد الفور iterations هذوما نجموا نعملوا كما نقولوا احنا a pattern ولا a tracing للامبليتيودز contained في الماركت element بتاع الليست بتاعتنا. يعني مع كل iteration في الاكس اكسس لهنا x axis denotes number of iterations، في y axis denotes the value contained في الماركت element في الليست اللي بنشتغل فيها. واللي نلاحظه انه as we increase the iterations the amplitudes increase بتاع الماركت element, then they decrease. So they increase, they reach a certain maximum and then they decrease. The amplitudes contained في الماركت element they decrease until hitting a certain minimum. لهنا كما قلنا نشتغل مع absolute value overall, and then we notice a certain increase once more. بالabsolute value it becomes a positive and it becomes an increasing value contained في الامبليتيود بتاع المارك element, and then we notice a certain decrease after a certain maximum and so on and so forth. فلهنا بنلاحظ انه في pattern of increasing hitting a certain maximum and then decreasing hitting a certain minimum and so on and so forth في value contained في marked element. So what we really did here, we tried to, if you will, we tried to attribute احنا حاولنا انه نعطيه values للmarked element في الليست بتاعنا على اساس انه element هذاك يكون as big as possible to distinguish the marked element, to make it special, to discover the marked element from الجيم بتاعنا. الانتويشن هذه ولا الجيم هذه will help us to understand the actual Grover search algorithm. So before we move on, does anyone have a question about the game? Okay, can move on. يعني الجيم بتاعنا هنا احنا حاولنا انه we conduct a certain search على element معين. element هذاك هو a marked element, a search element, a special element في السيرش بتاعنا. والبروسيس بتاع applying query then inversion then query then inversion in the form of consecutive iterations خول لنا انه we increase the amplitude contained in the marked element as much as possible. يعني عملنا increase الامبليتيودز بتاع الماركed element so that we increase it to a certain maximum and distinguish it so that we know which element is marked from the elements right here. And the Grover search algorithm, الالجوريثم بتاع Grover will function in a certain same way or a certain analogous way. So we are given an unordered list. The unordered aspect of the Grover search algorithm is very important. A certain unordered list وإلا بصفة عامة unordered space of search ولا space of possible solutions or possible trials. And we are going to make a search for a specific element في الليست بتاعنا which is marked ولا search for ولا special. We don't know احنا ما عندناش فكره ولا ما نعرفش انه اي element is marked and which element is not marked or unmarked. But we are going to conduct a certain search for a specific element called as marked. And we have n elements في الليست بتاعنا. Thus to encode these elements or to represent these elements في a certain quantum state ولا quantum superposition هنحتاج log 2 of n qubits. لأنه إذا كان عندنا n qubits الفيكتور بتاع الفيكتور that will represent the quantum state will be 2 to the power of n long. It will have 2 to the power of n possible quantum basis states. Thus 2 to the power of n amplitudes contained في الفيكتور بتاعنا. يعني we have 2 to the power of n slots or 2 to the power of n places to store our values that were once in our list. The values اللي they were contained في الليست بتاعنا هناخدهم هنعمل لهم representation في الكيوبيت representation بتاعنا. وكل base state كل amplitude corresponding to each base state will represent the list entries and will be accessing the list, will be interacting with the list. Interaction مع الليست هتكون with an intermediary of the oracle. The oracular programming or the oracular principles اللي شفناهم في السيشن الفايته هنستعملهم في السيشن هذه عشان we establish the interaction between us and the list. لأنه كما قلنا marked elements we do not know which elements are marked. We are going to find them with the Grover search algorithm. لكن interactions with the list to query some informations ولا to extract some informations من الليست بتاعنا هتكون via the oracle. Once the search element is detected, the oracle will execute a certain functionality or a certain application اللي هي similar to the query phase right here. Similar to the sign inversion that we did in the first phase of every iteration. And the oracle will flip the sign, will execute this query functionality for the corresponding amplitude, of the marked base state, that corresponds to the marked element in our list. At the beginning, to satisfy الكونديشن اللي حدثنا عنها هنا في الجيم بتاعنا انه كل entry في الليست بتاعنا هتكون في equal value ولا the same value initially. To satisfy this condition we will be applying the Hadamard operator. ليش؟ لانه الهادامارد operator يخول لنا ان نصنع a certain equal superposition. A superposition where every amplitude في superposition بتاعنا هتكون equal in its value, which will be equivalent to saying we started with a list of n elements with equal values, but in a quantum format. Thus, amplitudes بتاعنا هتبتدي في value 1 over square root of n, with n being the number of entries of our list, while the number of quantum base states, the same number. And as the game iterates, as we iterate our Grover search algorithm, which will have similar phases than with this game, as the game iterates, الامبليتيودز بتاعنا هيتغيروا هتصير evolution للامبليتيودز بتاعنا، والايفولوشن is required انها تعطينا outcome like the first outcome of the first iteration ولا the second iteration outcome. An outcome where the marked elements have a way higher value than the unmarked elements. فهذه يعني كان overview الجروفر search algorithm so that we stay on track so تكون عندنا فكرة على الالجوريثم هذا. And now we are going to introduce it with the utmost detail, with the maximum detail possible. فيعني does anyone have a question قبل ما نكمل؟ Perfect. Okay. Grover search algorithm في السيشن بتاعنا هنكتشف 3 parts of our session. The first part we are going to dive deep وهنفهم مع بعض the oracular approaches of quantum computation وكيف هنستعمل oracular approaches oracular computing في الجروفر search algorithm. The second part is the amplitude amplification. How can we harness oracular approaches to execute a certain functionality to increase the amplitudes of the marked elements or the special elements in our list? And هنكتشف as a third step the collection or the integration of all these parts in the Grover algorithm. هنعمل integration بتاع الموديولز ولا parts هذوما in the form of the Grover search algorithm. So a little overview على oracular approaches اللي عملنا لها introduction في السيشن الفايتة. For classical functions, classical transformations, we have a classical input which in the form of bit strings. For example, على سبيل المثال, f of x equals y, which is a classical function. It will take a certain input x, which is a certain bit string, and will output a certain bit string as output. لكن في quantum inputs, in the case of oracles right here, هيكون في input of a wave function which is a superposition of quantum-based states. The wave function here could be 2 qubits. It could be constructed of 2 qubit quantum-based states, ket 00, ket 01, ket 10, and ket 11, with corresponding amplitudes. وإلا تقدر تكون n qubits, with ket psi being the sum of each and every possible quantum-based state for the n qubit system, which is represented right here, ket I, with I being a bit string, a n long bit string, with every bit being 0 or 1, possibly. Okay, our input, as we said, is a superposition of all quantum-based states. A superposition of all quantum-based states or some quantum-based states, but it is a superposition, a wave function for our quantum function or quantum transformation, which is the example of the oracle. The oracle هنا هو special operator, a special quantum operator, or a special quantum tool, which is a black box from the executor point of view, a black box that performs a certain task of computation. So there is هنا في 2 points of view. From the executor point of view, from the point of view of the executor, of the person اللي هتعمل execution بتاع الاوراكل، الشخص هنا ما يعرفش الكونستراكشن والا الفانكشناليتي بتاع اليو اوف اف. الاوراكل هنا اليو اوف اف is invisible for the executor point of view. لكن from a conceptor point of view, from the person who will concept and will create this oracle, which is composed of unitary operators of quantum gates, the conceptor knows the functionality of the oracle because he will concept it, he will create it from scratch. So from the conceptor point of view, it is understood, the functionality of the oracle is understood, but from the executor point of view, the هنا ما بيعرفش الستراكشر بتاع الاوراكل، لكن هو يعرف حاجة واحدة. إذا هو بيعمل query للاوراكل هنا, he will get a certain result out of it. The query will give him a certain result, a certain outcome, والoutcome هذا هيكون يعني ليه اهميه في الكومبيوتيشن ولا في الالجوريزمز اللي in general ولا في الكلوفرسل algorithm النهارده. Okay, the general form of oracles as we saw في السيشن اللي فاتت انه oracles have two inputs, two quantum states or two quantum systems as input, kit x and kit y. In general kit y here حتكون qubit واحد, but kit of x can be one qubit والا n qubit system. And kit of x will not be changed by the oracle. This is very important to understand. Kit of x under the impact of the oracle will not be changed. مش حتتبدل. بس الكيت اوف واي هي اللي حتتبدل. الامباكت بتاع الاوراكل حيكون واضح في الكيت اوف واي, which is the fundamental conception of the oracle or the concept of the oracle. انه الكيت of x will just guide the application of a certain function f of x على second quantum state or second quantum superposition kit of y, which is usually a one qubit system. Oracles, just some remarks about the oracles. Oracles are unitary operators like the quantum gates لأنهم أصلا متكونين من a collection of quantum gates which are unitary and reversible. And the oracles can do two things. It can perform some sort of computation. هي تقدر تعمل computation of some sort, وتقدر تعمل a marking of a certain correct answer. The oracle, if designed correctly of course, تقدر تعمل الماركينج ولا الهايلايتنج بتاع الكوريكت انسر, واللي هي الفيرست phase of our game, the same task of the first phase of our game that we introduced في the beginning of our session. For example, let's find out about some computation of the oracle, but this examples هنا حيكونوا حيعاونونا عشان نعمق فهمنا للاورacles. بس الاورacles في الجروفر سيرش algorithm will be mainly used for the marking of a correct answer. بس هنا for some examples we have an input kit of x, kit of y, a certain oracle. بس هنا الفانكشن f of x will always output 1. So هنا في ال general principle of the oracles, the oracle will take a certain input kit of x وحتعمل الفانكشن f of x, بس حتاخد البيت سترينج بتاع x as input. هي حتاخد البيت سترينج هنا في الفيرست كوانتم ستيت, first input quantum state بتاع الاوراكل, حتعمل له application بتاع f of x, وحتعمل the XOR operation that we saw in the previous session, وحتى تعمل output بتاع الكوانتم state the corresponding quantum state. بس هنا هناخد الفانكشن f of x, الفانكشن بتاعنا حتى تعمل output دايما 1. So f of 0 is equal to 1, f of 1 is equal to 1. Does anyone have a question? Okay. Okay. So the function, as we said, is a constant function هنا. وحنلاحظ from the truth table right here, and f of x XOR y will always output the inverse of the value contained in the y bit. فيعني إذا كان ال y 0, the output of the XOR operation will be 1, and if the y value is 1, the output will be 0. عشان نعمل conception of our oracle, the corresponding oracle that gives us results هذا, from the conceptual point of view. Okay, no one has a question. From the conceptual point of view, the conceptor will put the x gate for the kit y quantum state. لأنه هنا الأكشن بتاع الأوراكل is visible ولا is constated just في ال second quantum state ولا second bit ولا second quantum register في ال quantum programming afterwards. فيعني الأوراكل هنا حتكون just a not operator ولا x gate على الكيت y عشان تعمل output بتاع kit f of x XOR y, which is 0 becomes 1 and 1 becomes 0. So this is from the conceptual point of view, but from the executor point of view, the executor will not see the x gate. هو حيشوف just an oracle, a black box, and from queries from that black box the conceptor will begin to understand الفانكشننج بتاع الاوراكل وهيكون له interaction مع الاوراكل على شكل queries. He will query the oracle to get some information from it. For a certain other example, for the oracle, for a certain other example for our oracle, هيكون يعني الفانكشن f will always output the inverse of the input. So f of 0 هيكون 1 و f of 1 هيكون 0. ولما نعمل truth table بتاعنا x and y and the corresponding values, it will give us this particular value, this particular full configuration. The configuration هذه is equivalent to applying the C0 operator, where the second quantum register بتاعنا هيكون التارجت بتاع C0 والfirst quantum register هيكون control, the register اللي هيعمل control على الابلكيشن بتاع not operator على second quantum register. So إذا كان نعمل C0 هذه هيكون الاوتبوت 0 1 1 0 علشان النوت اوبريشن تكون ابلايد على السكند ريجستر لازم الفيرست ريجستر يكون 1. يعني الاوتبوت هيكون 0 1 in the case of x being 0 and 1 0 which is the inverse of 0 1 وفي وقت الانبوت وقت الفيرست كوانتم ريجستر يكون 1. بس هنا هو الانفرس بتاع الاكشوال اوتكم فيعني لازم نزيده another x gate. So 0 0 1 1 here as the control gate as the control qubit. Y is the target qubit. If we apply the C0 it becomes from 0 1 0 1 it becomes 0 1 1 0 under the impact of the C0 operator. And if we want to reach this particular outcome, the 0110 must undergo another X gate, another quantum NOT gate or quantum inversion to become 1001. So this is the conception of our oracle. And from the executor point of view, he will not see these two quantum gates, the 2 qubit quantum gate and then the 1 qubit quantum gate. He will see only an oracle, and the only interaction between the executor بتاعنا and the oracle will be in the form of queries. هو هيعمل queries للاوراكل عشان ياخد information من الاوراكل بتاعنا. فقبل ما نمر للفيس فليب اوراكل وفي هنا examples في النوت بوك بتاعنا هو في examples and في imports عشان اللي ما فيش يعني ما عملش installation بتاع Qiskit and some other libraries you can find them right here. And there is a certain function, this is a bit list, the bit list function that returns all possible bit strings of length, number of bits, all possible bit strings, and the checking of the truth table that will be important for us right now. يعني هون في النوت بوك بتاعنا هيكون في implementation of some examples of oracular programming or oracular conception of some problems or some function that will be encoded under the form of a certain oracle. فهنا مثلا الاوراكل بتاعنا will output always the bit y. So 01 01 will always be 01 01 واحنا قلنا انه second quantum register ولا second quantum state ولا second bit get y will be the reference of our conception of our oracle. فيعني هنا الاوراcle didn't change anything around anything at all في ال second register. So 0101 stayed 0101. There is no change. Thus the oracle هنا ما بتعملش حاجة أبدا لأنه ال f of x XOR y will not be changed from the initial y register. فيعني هنا الاوراكل هتكون empty ما تعمل حتى حاجه. و if you want to check with a truth table with this predefined function will check with the oracle اللي بنيناه احنا هتعمل التروث تيبل بتاع الاوراكل اللي عملنا له الكونسبشن لحد دلوقتي. وهنعمل يعني تشيكينج ما بين الاوريجينال تروث تيبل والتشيك تروث تيبل بتاع الاوراكل اللي عملنا له الكونسبشن. وحسب ما نشوف هنا الاوراكل بتاعنا تعمل نفس التروث تيبل اللي طلبناه في الفيرست اكزامبل. So 0101 state 0 1 0 1 right here. Another example, this is another example of the oracle which implements a certain, if you will, function f, balanced function here. The output of the oracle or the XOR operation will be 0 1 1 0, corresponding to these two inputs, the x and the y inputs. And this is actually corresponding to an application of the C not operator ولا the control not operator. لأنه هنا لما الاكس تكون واحد هتكون في ابلكيشن بتاع الاكس جيت على الواي ريجستر. فيعني هنا لما الاكس هتكون 0 الواي ما بتاثرش ما بتاثرش ابدا 0 1. بس لما تكون الاكس ايكوال 1 الواي هتكون في انفرجن للبيت سترينج بتاعها. فهي كانت 0 هتبقى 1 and كانت 1 هتبقى 0. فالاوتبوت بتاعنا final output will be 0 1 1 0 which is equivalent to our demanded truth table. فيعني الاوراكل هنا هتكون في conception بتاع C not في وسط الاوراكل و we can check with our truth table 0 1 1 0 as we demanded. And there is هنا في three questions to better practice with the concept of oracular design. فيعني هنا عملنا overview على how to design oracles, how to think about designing oracles from the conceptual point of view. This is very important so that the executor afterwards can execute and get some information out of it. Does anyone have a question about this part? Excellent. Okay. Now let's move on to the phase flip oracle. فهنا الاورacles اللي عملناهم قبل شويه the two examples والاكزامبلز في النوت بوك بتاعنا هم really oracles that perform a sort of computation. الاورacles هنا عندهم function f وهيعملوا some computation ولا some change على السكند register ولا السكند quantum state get to y following ولا depending on الفانكشن اللي عندهم f والاوتبوت بتاعها. بس هنا هنعتمد another type of oracles that mark a certain element. الاوراكل هنا هتاخد superposition which is the quantum analog ولا quantum equivalent بتاع الليست اللي تحدثنا عنها قبل شويه. هياخد السوبربوزيشن بتاعه وهيعمل phase flip، هيعمل inversion للساين بتاع الماركت elements ولا الماركت quantum states which is analogous to the query phase اللي عملناها قبل شويه. The inversion of the amplitudes corresponding to the marked elements in our list. فهنا the phase flip oracle does just that and it needs a certain function. In general the phase flip oracle will receive a certain function. هي هتاخد function f والfunction f هنا هتكون يعني فيها information ولا فيها description للتاسك بتاع السيرش بتاعنا. And we can use الاوراكل بتاعنا to execute the research task اللي هنعملها with the function f. And this function f as we said هي هتكون فيها definition ولا هتكون فيها some information على التاسك بتاعنا، التاسك بتاع السيرش. فالفانكشن f that depends from the task بتاعنا بتاعت السيرش هتكون implemented through the oracle. And from the executor point of view الاكزيكيوتر هياخد الاوراكل هذه وهيستعملها عشان يعمل الكويري فيز اللي تحدثنا عنها، الانالوج بتاع الكويري فيز في الجروفر سيرش الجوريثم اللي هيعمل ديتكشن بتاع الماركت اليمنت وهيحضره للستيب الثاني في الجروفر سيرش الجوريثم. In general, as we said, the function f will have a certain input, which is elements بتاع السيرش بتاعنا، الاليمنتس اللي احنا نعمل execution بتاع السيرش عليهم، وهيكون كان في some output where f of x right here x هيكون هو يعني possible input ولا possible solution، واذا كان السولوشن هذه صحيحه هيعمل output بتاع value 1 if the x is the search element or search elements eventually هيعمل output بتاع 0 otherwise if the x is not a searched solution. And from this particular configuration عملنا encoding بتاع السيرش تاسك بتاعنا successfully with this function f of x. For example هنا هنعمل introduction بتاع a certain problem which is the traveling salesman problem. والبروبلم simple قوي في الديفينيشن بتاعه يعني. هنبتدي من city A هو يعني في collection بتاع cities A B C and D والcities هذول يعني مربوطين بpaths ولا highways if you will. وكل highway كل يعني طريق هيكون فيه cost بتاع kilometers ولا بتاع duration of traversing this path. We don't care, but there is a certain cost which is 100 200 300 etc. والسيزمن بتاعنا هيبتدي من city A هو عاوز يزور كل other city عاوز يزور city B C and D exactly once وعاوز يرجع للcity A without if you will exceeding the total distance of 900. So he will be starting in A. He wants to visit every single city once, exactly once, and return to A without exceeding the distance of 900. For example, if he starts in A and then goes to C, A, C, D, B, A, this is a valid solution if the path is less than 900. So 200 plus 300 plus 400 plus 100 is 1000. So it is not a valid solution. But if we do A, B, C, D, A, هو يبتدي من city A يروح ل B then C then D then returns to A. The distance will be I believe 800. So 100 plus 100 plus 300 plus 300 is 800. So A, B, C, D, A, this possible solution, this possible trial is correct. فيعني in our conception or in our creation of the function f, f of A, B, C, D, A must be equal to 1 and f of other paths must be equal to 0 so that our function f will encode our problem successfully. Our function f will afterwards be used in our oracle to do some sort of phase flip to highlight the marked elements. فيعني in general our function f here هيكون في information ولا هيكون في details على البروبلم بتاعنا زي هنا traveling salesman problem. Our function f details the marked and unmarked elements ولا the searched and unsearched elements ولا the important and correct elements and incorrect elements. بس from the executor point of view our executor doesn't know anything at all على الفانكشن بتاعنا f بس هو عنده oracle والاوراكل هذه هيكون في possibility بتاع interaction between them such as the oracle will give them some output depending on the query بتاع الاكزيكيوتر. فيعني الاوراكل هنا ما توريش السولوشن للاكزيكيوتر بس الاكزيكيوتر يقدر ياخد شويه information من الاوراكل in the form of queries. والاوراكل هنا هيكون في integration في الفانكشن بتاعنا if اللي تعمل encoding ولا تعمل encapsulation if you will للبروبلم بتاعنا and it will be used afterwards في oracular format or oracular general format of get y becoming get of f of x XOR y will other register will not be affected. So for this task, for the task of highlighting the marked elements in our superposition, هنستعمل particular type of oracles واللي هو the phase flip oracle to execute the first part of our algorithm, the part of the query اللي تحدثنا عنه في أول السيشن. الquery اللي تعمل inversion ولا تعمل it includes a minus sign ولا it introduces a minus sign للmarked elements بتاعنا. هنا ال U of f will be using a certain oracle كما تحدثنا. ال f عندنا a function that encodes the problem and it will be introduced لل U of f اللي هي the oracle. بس هنا هيكون في input special شوية. The kit of y will always be kit minus which is 1 over square root of 2 times kit 0 minus kit 1. Well, kit minus is the result of applying the Hadamard mark to the kit 1 base state. Just an information هنا. فيعني get y the second input of our oracle will always be get minus. واذا كان عاوزين نعمل application بتاع الاوراكل هيكون في two inputs as we said u of f and get x get minus, and we can do some calculation. نقدر نعمل شويه calculation عشان نفهم اكثر الامباكت بتاع الاوراكل على التو كيوبيت سيستمز بتاعنا. يعني اليو of f with the first input get of x will not be touched, but here we will be هنعمل just detailing ولا هنعمل just expansion بتاع ال get minus وال second input هنا. بعدين هنعمل just distribution على ال first part of our oracular input. So it will be u of f get x will be distributed to get 0 get 1. So it will be u of f get x get 0 إلا u of f get x get 1 with the 1 over square root of 2 factor getting out. وحسب الجنرال فورمات بتاع الاوراكل this particular input will be get of x f of x the application of the function f على البيت string x XOR 0. from our information for your information a certain property about the XOR operation إذا كان عندنا يعني input 0 في ال XOR operation the output will be always equal to the first input. فيعني إذا كان ال b is equal to 0 the output will always be a. So 0 XOR 0 will be 0, 1 XOR 0 will be 1. So 0 is a neutral element في ال XOR operation. فيعني إذا كان عندنا 0 في ال b الاوتبوت بتاع ال XOR operation will always be a, the value contained in a, that is. So فيعني f of x XOR 0 will always be equal to f of x. بس هنا f of x XOR 1 is not changed because we don't know what is the output. We just did here just the extraction of the get of x because it is a common factor in here في الاكسبريشن بتاعنا في two inputs. وهنا there is a certain important transition ما بين السطر هذا والسطر هذا, وانه ال get of x minus get f of x XOR 1 will always be equal to minus 1 minus 1 to the power of f of x get 0 get 1. You can check it for x the input x0 or the input x1, it will always be the same with the other scalar or with the other factor 1 over square root of 2, and this value will be equal to minus 1 power to the power of f of x get of x get minus. ونلاحظ هنا حاجة غريبة شوية اللي هنا under the impact of the oracle u of f the first quantum state get of x and the second quantum state get minus evolve to the value minus 1 to the power of f of x get x get minus. There is something strange here. في حاجة غريبة لأنه هنا normal thing ولا normal outcome هو أنه the second quantum state will be changed under the impact of the oracle. So get of y will become get of f of x XOR y, well first quantum state will not be changed. بس هنا في output غريب شوية. The first quantum state or the first quantum register in the language of quantum programming will be affected, will be changed, but the second input will not be changed. The inverse of the supposed impact of our quantum oracle. هنا بيظهر الفينومينون بتاع الفيز كيك باك. هنا في phase ولا في factor that was supposed to appear في ال second register لكن it was kickbacked, it was thrown to the first quantum state or the first quantum register and it appeared there. So الظهور بتاع الفيز كيك باك ولا الظهور بتاع impact in general of the oracle ما ظهرش في ال second quantum state بس هو ظهر في ال first quantum state in the form of a certain factor minus 1 to the power of f of x. And we notice when f of x is equal to 1, when the outcome of f applied on the bit string x will be equal to 1, في phase ولا في scalar ولا في a certain value of minus 1 will be kicked back ولا will be appearing in the first register or first quantum state. with the result of being it a certain sign flip effect. So the sign of the first quantum state will be flipped, will be inversed from positive to minus. And here, with the application of the oracle, we succeeded in applying a phase flip for the first quantum register. And in the quantum search algorithm, the Grover search algorithm, this is important لأنه with the information of F, we do not know anything about F. لكن هنا بالintermediary بتاع الاوراكل قولت لنا ان نعمل ابلكيشن بتاع الماينس 1 هنا على الفيرست كوانتم ريجستر اذا ال f of x is equal to 1, which is equivalent to saying that اذا كان ال first quantum state is a marked quantum state, a correct solution, there is an application of a phase flip that will appear in the first quantum state also. يعني الاوراكل هنا بالinformation that is contained in the function f, which is, I repeat, is not visible من point of view بتاع executor, it is only visible من point of view بتاع الconceptor بتاع الاوراكل. بس من point of view بتاع executor, he doesn't know anything about the function f, he doesn't know anything about element اللي احنا we want to do the search on ولا we want to find out. بس هنا with the application of the oracle, the executor was successful in applying a phase flip while applying a minus sign for the first quantum register or the first quantum state if the first quantum state is a marked quantum state, which is equivalent to saying if f of x is equal to 1, that is x is a marked state. And this is all done without any knowledge of the function f, which is the power of the oracle. The oracle هنا ما عملت لنا حتى يعني حتى لمح ولا حتى idea ولا حتى يعني تلميحة على ال value contained in f of x ولا structure بتاع ال f. بس هنا it only from our query, من الكويري بتاعنا اللي عملناها على الاوراكل, it introduced a minus sign ولا a phase kickback in the form of the minus sign on the first register if the first register or if the first quantum state is marked. وإذا كان نحب نعمل a certain visualization of the phase flip oracle, we can represent our quantum state as the sum of kit V and kit W. Kit W is the target quantum state, the searched quantum state or the searched outcome in the form of a quantum state. Kit V is the superposition of all other outcomes. So you can see it from this particular summation. The summation هذه تقدروا تشوفوا انه ال I, which is from 00000001 to all possible quantum base states في n qubit system بتاعنا. بس ال kit W is excluded here, ما بتظهرش في السم بتاع kit V. So it is a superposition of all non-target states ولا non-marked elements like the terminology اللي استعملناها في أول السيشن. فال kit psi, which is our starting quantum state or our random quantum state, هي في الميدل بتاع ال superposition of target of the target state and the superposition of all the unmarked elements ولا non-target states. والapplication of the phase flip oracle will flip the phase of the quantum base states if these quantum base states are marked. فيعني ال amplitudes corresponding to the marked elements will be flipped. But the values correspond, or the amplitudes corresponding to the unmarked quantum base states will not be flipped. But this corresponds to this particular coordinate will be flipped, or it will acquire a minus sign. وفي يعني minus sign هيكون apparent في الفاليو هنا ولا في الكوردينيت بتاع الكيت بساي على الاكسس بتاع التارجت ستيت, and it will be transformed to this particular state and the other values will not be changed علشان هم يعني ما همش marked يعني. فيعني it flipped us to the new state u kit psi, which is the new state resulting from the phase flip oracle, which is the a certain reflection alongside the x-axis, which is the state kit V. وإذا كان عندنا برشا يعني كان عندنا اكثر من تارجت element ولا اكثر من تارجت كوانتم بيس ستيت. فيعني التقسيمه تكون على two subspaces: the target subspace ولا the marked subspace kit omega, which is the summation of all the marked elements divided, of course, by the coefficient of normalization of the quantum state, the condition of the unitary vector of a certain the vector being unitary of our quantum state, will get V, which is the summation or the superposition of all unmarked or non-target quantum subspaces, and the action تقعد هي نفسها the reflection alongside this particular axis, the axis بتاع الكت V, which is the superposition of all unmarked quantum states. هذه هي action بتاع oracle face flip oracle. So ket W here is the superposition of all target states, وهنا الكت V هي superposition بتاع all the untargeted states ولا unmarked states. For example هناخد example هنا نفهم به الاكشن بتاع الاوراكل الفيس فليب اوراكل. عندنا هنا n equal 8 وعندنا هنا يعني 8 entries of our list in the terminology of our example or our game that we introduced في البداية بتاع الحصة, which is equivalent to saying that we have 8 quantum base states ولا 8 possible elements. These 8 elements, we do not know if they are marked or unmarked from the executor point of view, with 3 marked elements from the conceptor point of view. So the conceptor created a certain game or a certain search task where the 3 search elements are the 3rd, 4th, and 7th elements بتاع الquantum base states ket 000 ket 001 حتى الكت 111. ونقدر نستعمل الكيوبتس بتاعنا to associate each element بتاع الليست اللي تحدثنا عنها ولا possible outcomes بتاعنا to all quantum base states with the 3rd, 4th, and 7th being marked. وبنبتدي with a certain quantum state, a superposition which is equal زي ما تحدثنا قبل شويه, which is equivalent to saying we applied the Hadamard on each and every qubit ولا each and every quantum bit, واللي حيعطينا an equal 8 quantum state superposition ولا an equal 3 qubit system superposition, 1 over square root of 1 over 2 square root of 2 for each and every quantum base state, and the summation here is an equal superposition. And this is the input بتاع الاوراكل face flip oracle بتاعنا. Under the impact of the oracle, the marked elements here, the 3rd, 4th, and 7th elements will be inverted. The phase contained, well, the sign of these elements will be inverted, will be flipped from plus to minus. So يعني الكت 010, the 3rd element will be inverted right here. The kit 011 will be inverted. والkit هنا kit 110 the sign بتاعه هيكون inverted as well. This is the result of applying the oracle, the phase flip oracle, on kit of x for every quantum base state possible in our superposition. قبل ما نمر للcoding notebooks, does anyone have a question? Okay, we can move on. هنا بنقدر نعمل definition لعديد الفيز flip oracles. فهنا for example the conceptor wants to create an oracle, هو عاوز يصنع oracle اللي بتعمل phase flip للتارجت ستيت 01 كت 01 that is. فيعني هنا هيعمل definition للاوراكل بتاعه عشان يعمل phase flip ولا sign flip للكت 01 quantum state which corresponds to the target state kit 01. فيعني هنا الكرييشن بتاع الكوانتم سيركت موجوده في النوت بوك, بس it's more clear or it's clearer to understand with the circuit output. فيعني هنا For the 3 qubit system هنا عنده 2 qubits for the target states or the X register والkit Y register will contain 1 qubit. هنا الkit Y فيه 1 qubit والtarget state هنا عنده kit 0 1. هنا he will apply a order بتاع التارجت state will be flipped عشان يعمل matching with the Qiskit bit ordering. فهنا يعني الكيسكت نقدر نفهمها مع بعض. هنا هو عاوز يعمل يعني detection للquantum target state kit 0 1 بس هنا لازم يعمل inversion عشان الكيسكت بيشتغل باوردر عكس الاوردر بتاع الرايتنج بتاع الكوانتم quantum states. سوري هنا if we have kit 0 1 الكيسكت مش هيفهمها 0 1 right here. هنا this is the first qubit and this is the second qubit. هنا الكيوبت رقم 1 والكيوبت رقم 2 في الاكسبريشن بتاعنا. بس هنا في الكيسكت هو مش هيعمل association between the first qubit in the quantum register Q0 first entry of quantum register Q0 and Q1 مش هيكون the second qubit. لا هو هيعمل association كده 1 0. فيعني الكيوبيتس الاوردر بتاع الكيوبيتس هيكون inverted. فيعني it's necessary انه نعمله reversing للاوردر بتاع التارجت ستيت عندنا هنا. وهنا الاوراكل بتاعنا لازم يكون تعطي اوتبوت بتاع الاوتبوت هنا في الانسيلا كيوبيت ولا في السكند ريجستر كيت واي corresponding to the input kit 01. فيعني اذا كان عندنا input kit 00 سوري عندنا input kit 00 the C not operation هنا مش هتشتغل عشان some operations will prohibit it from functioning in our quantum circuit. فالفيرست ستيب بتاع designing ولا creating a certain quantum circuit or a certain quantum circuit that encodes the code phase flip oracle هو ال preparation بتاع الانسيلا كيوبيت ولا السكند second register which is kit y in the kit minus state زي ما اتكلمنا هنا as the first condition. The phase flip oracle عندها property special شوية انه الكت y must be equal to kit minus for the phenomenon of phase kickback and the appearance بتاع minus 1 في first register to be possible of course. يعني هنا it will apply the ancilla ولا prepare the ancilla في state kit minus وبعد ما تعمل preparation هتعمل application of Hadamard operator on all the main qubits, not the ancilla qubits included. لا, the qubits بتاع first register, which is the kit X register, to be in a complete superposition. To create the superposition that we talked about, this is a 3 qubit superposition, but this is an equal superposition, which is the starting point بتاع الجروفر search algorithm والapplication بتاع الجروفر search algorithm اللي هنعمله في السيركت كده. فيعني هنا this equivalent to x then h. احنا اتكلمنا وقلنا قبل شويه انه kit minus is the application of the Hadamard on the kit 1 state and every quantum circuit starts with kit 0 for every qubit. فيعني لازم نعمل application بتاع x gate then the Hadamard gate عشان kit 0 becomes kit minus. This is the ancilla qubit and these are the ancilla qubit ولا kit y qubit. And these are the kit of X register. But with the order of Qiskit, not the order of the theoretical writing that is. وبس هنا نعمل Hadamard على ال entries بتاع ال first register for the Q1 register which is equivalent to the first qubit هنعمل the X gate ولا the not operator. ليش؟ لأنه هنا احنا عاوزين السي نوت تشتغل وتعمل ابلكيشن بتاع الانفرجن هنا على الانسيلا كيوبيت على السكند كوانتم ريجستر اذا the two x register والا اذا الفيرست ريجستر في الستيت كت 01. فهنا لازم نعمل ابلكيشن على الاكس جيت هنا عشان تبقى 0 تبقى 1، وعشان هنا في الكنترول يكون هنا 1 يكون هنا 1، فالسي نوت بتشتغل هنا وتعمل الابلكيشن بتاع النوت اوبريشن على الانسيلا كيوبت، وتعمل الابلكيشن بعدين بتاع الفيس فليب على الفيرست ريجستر. فيعني هنا فور اكزامبل اذا كان بنعمل input بتاع another state not get 01. If we have for example get 00, so the first register هنا عندنا هيكون get 00، فيعني هنا هيكون 0 وهنا هيكون 0. هنا هيكون في application بتاع هذا مارت، وهنا هيكون في application بتاع not operator such as الابلكيشن بتاع application بتاع C not operator will receive 0 1. This is get 00, a part of the superposition created by the two Hadamars right here, one of the four quantum based states or four possible quantum based states. وبعد X gate الكت 00 it becomes input 00 هنا هيبقى 0 هنا 1 هنا. السي نوت مش هتشتغل، والابلكيشن بتاع الفيس فليب والابلكيشن بتاع الماينس على الفيرست ريجستر will not be applied. بس لما بنعمل هنا في الانبوت بتاع 1 0 مثلا، لنا هيبقى 1 ولنا هيبقى 1، فالسي نوت هتشتغل، والفيس فليب ولا الابلكيشن بتاع الماينس 1 تو ذا باور الابلكيشن بتاع الماينس 1 هتكون فاليد، وهيكون في فيس فليب ولا هتكون في فليبنج بتاع الفيس بتاع الفيرست ريجستر. اذا كان مثلا نعمل 0 وهنا نعمل 1، هنا هيكون في 0 وهنا هيكون في 0، السي نوت مش هتشتغل برضه. واذا كان نعمل هنا 1 1، the fourth الفورث possibility بتاعت السوبربوزيشن كرييتد التو هذا مالز هنا هيكون في لنا 1 ولنا هيكون في 0. سو السي نوت مش هتشتغل، والاف اوف اكس مش هتعطينا يعني ماينس ساين على الفيرست ريجستر، بس it is not a it is not a marked element ولا it is not a search element, and then it will be ignored by the oracle of the face flip oracle. فيعني هنا الايديشن ولا الايديا behind the preparing the quantum circuit in this order of the X gate where the target states have 0. فيعني هنا الفيرست qubit has 0، فالcorresponding quantum register place of this first qubit will contain X, so that when we have an input of 0 01 من الهدمات من الايكوال سوبربوزيشن offered by these two هدمات، الاكس هتعمل فليبنج للزيرو ترد 1، وال1 مش هيتاثر ابدا، والسي نوت هتشتغل، والاشتغال بتاع السي نوت هيأثر على الكوانتم بيست state that is searched right here and flip it to a minus sign يعني. And from this particular circuit بعد السي نوت هنعمل an application of the X gate to cancel الافكت بتاع الاكس جيت هنا عشان الكوانتم ريجستر انتري تعود للحاله الاصليه بتاعتها، وبعدين هنعمل هذا مر بعدين اكس عشان نعمل كانسليشن لل minus get minus state in the ancilla qubit. واذا كان نعمل display exact quantum states بعد الابلكيشن بتاع السيركت هذا، هنلاحظ الكوانتم ستيت هذه where the first entry of our quantum state هنا is the ancilla qubit. It will become it is always 0 عشان هنا عملنا الابلكيشن بتاع x then هذا then x it will return to its original state. بس هنا for the state where the x register which is get 01 هنا where the x gate is the x register is get 01 هنا بنلاحظ انه في فيس فليب ولا في ماينس ساين هنا ظهر لانه كت 01 is a marked element or a target state right here. فلان this function allows us to اننا ناخذ الاكزاكت كوانتم ستيت والاكزاكت كوانتم فورميليشن في الستيب هذه. واحنا بنلاحظ هنا انه كت 01 which is the first quantum register is ket 01, thus the minus sign appears right here, and for the other inputs they are not marked, هما مش search ولا مهمش targeted, thus we do not affect a minus sign. بنقدر نعمل a 4 qubit system ولا a 4 qubit quantum state or a 4 qubit superposition with a target state ket 0010, and the same reasoning here for the quantum registers entries where we have a certain 0 for the target state, we apply x, so that if we have 0010, we do not order it by saying 0010. No, in here. So, هذا ماردز هنا في كل entry بتاع الفيرست كوانتم ريجستر حيعطونا 2 to the power of 4 which are 16 quantum based state, quantum possible quantum based state that is. في كل quantum based state the oracle will function and will detect the marked quantum based state and flip its sign. And for 0 0 1 0 هنا حيكون في bit flip لهنا والا X gate which is the C not quantum not operator. The 0 will become 1 وهنا 1 will not be subjected to anything فتقعد 1 تبقى 1. 0 will become 1 and 0 will become 1 في ال Q3 which is the first qubit. Q3 is the first qubit, Q2 is the second qubit, Q1 is the third qubit, and Q0 is the fourth qubit. كده الريدنج دايركشن بتاع الكاسكيت وكده الريدنج دايركشن بتاع الكوانتم فورميليشن والكوانتم ثيوري اوف انفورميشن right here مثلا كده. فيعني we have 4 ones ولا 4 qubits in the state 1, so the C naught will be activated هنا, والاكتيفيشن بتاع C naught بتاثر على الانسيلا qubit so that the first quantum register ket of x will receive a minus sign, will receive a minus sign factor, and it will be marked as searched ولا as targeted. إذا كان مثلا بنجرب بالquantum state 0 1 1 1 فهنا هنبتدي 0 1 1 1 0 هتبقى 1 1 هتبقى 0 هنا لانه في اكس جيت 1 هتبقى 1 وال1 هتبقى 0. الاكس جيت السي نوت دي control the multiple control not operator will not be activated right here, so there will be no minus sign for first quantum register and there will be no highlighting quantum based state or quantum based state that corresponds to a quantum searched state. يعني هنا the second example was explained, وبالطبع نعملوا 3 x gates بعد الابلكيشن بتاع الفيرست x gates في Q0 Q2 و Q3 to cancel the impact بتاع الاكس جيت في ال 3 quantum register entries, وهنا بنعمل هذا مرة وبعدين الاكس جيت الQ4 to cancel the impact of the ket minus state على الكوانتم دي انسيلا كيوبيت ولا كيت واي ريجستر. وبنقدر برضو نعمله ديسبلاي ولا نعمله بروجيكشن للاكزاكت كوانتم ستيت ولا الاكزاكت كوانتم فورميليشن للكوانتم ستيت بعد الكوانتم سيركت هنا. وبنلاحظ انه first qubit is always the ancilla qubit في الكوانتم سيركتس هنا, بس الماينس ساين is applied when the x register ولا x ket of x is equal to ket 0010, exactly what we wanted here with the target state ket 0010. بس هنا عملنا definition ولا عملنا application لل quantum molecules that highlight just بس بالطبع حيكون في مشاركه للكود، وحيكون في مشاركه يعني للسولوشنز بتاع التاسكس هنا. فهنا في كويستشنز عشان بنفهم اكثر وبنعمل براكتس اكثر، وحيكون في مشاركه للكود والكوركشن بتاعه. بس هنا عملنا ديفينيشن الكوانتم اوريكل اللي تعمل هايلايتنج ل one quantum target state. هنا عندنا one quantum target state which indicates that we have one element to be searched في الكوانتم سيرش بتاعنا. بس in general we can have 2, 3, 4 and even more quantum states to be searched. So we need to define oracles that highlight many search elements in our circuits. وهنا بنقدر نعمل oracles that highlight two quantum states, Kit 001 and Kit 101 for 3 qubit systems. You can try if you want to create such an oracle, but the solution will be shared with you after the end of the session. But it's better and it's more intuitive and more beneficial if you think about it. حاولوا تفكروا فيها عشان هو يعني it's a very helpful exercise. حتى لو كان ما تلقاوش solution, the act of thinking or act of finding a solution and it is more beneficial, ويزيد يفهم الإنسان أكثر وأكثر الماتيريال at hand. Try to think about it with theoretical formulation. هنا عملنا الانترودكشن how can we think about the phase flip oracles. بس انتم بتقدروا تعملوا oracles بتاعكم بنفس الريزنينج، بنفس الميثودولوجي يعني. و you can check your results or you can check your oracles with the theoretical steps that we introduced right now. We can also introduce clear these up. And we can also introduce a general format for our oracles. هنا عملنا definition الأوراكل لكل يعني example بتاع target state. For the target state Kit 00 ولا Kit 01 هنا for the 2 qubit systems we defined an oracle. For the Kit 0010 target state for 4 qubit systems we defined an oracle. بس هنا هنحاول نعمل definition, a general definition الأوراكل that takes a certain target state. هنا هتاخد quantum circuit بتاعها وهتزيد على الكوانتم سيركت بتاعها الاوبريتورز دي many control gates وال1 qubit gates. It will take a target state, will take a target quantum base state, and it will take the ancilla qubit that will work with it, well, the second register or the Kit Y register that we will be working with. It will extract the number of qubits or the number of the main qubits right here, and it will add the X gates for every placement where the target state has a zero. نفس الريزنينج هنا. فهنا عندنا target state Kit 0010. If we lie it with the quantum circuit representation it will be 0010. ففي كل مكان اللي عندنا فيه زيرو في التارجت ستيت بنحط اكس بعد الهادامارتس بالطبع، لانه الهادامارتس هم اللي يعملوا الكرييشن بتاع الايكوال سوبربوزيشن. This equal superposition between all possible quantum states is created by the 4 hadamarts, and these X gates الاكس جيتس هذوما هيعملوا كل فلتر ولا هيعملوا كل سelection الكوانتم بيس ستيت that is searched ولا that is marked so that the minus sign will be applied to them. So between one of these quantum states that were resulted in these hadamars is the 0010, and we want to mark 0010. This is from the conceptor point of view. I repeat, this is not from the executor point of view. The creation of the oracle is from the conceptor point of view. The executor just does queries and receives information from these queries so that he can proceed. بس هنا إذا كان عنده input 0010 the X gates will flip the zeros to ones, and here nothing that is equivalent to saying that we have a 1 here, so it will be activated. And from the C0 operation, the multiple control C0 operator right here, I have 4 controls, and if those 4 controls are in state Kit 1, the not operation will be applied on the ancilla qubit, and that will activate the minus sign on the first quantum register. So here ideation behind the oracle creation of the Grover search algorithm. And afterwards we apply the same application of the X gates. هنا بنعمل X gate هنا ولا أنا ما نعمل حاجينا خاطر هنا ما ماليش ابلكيشن بتاع الاكس جيت. بنعمل 2 اكس جيتس for Q2 and Q3. وهنا بنعمل هذا مارك and then X because the ancilla was set to ket minus هنا, فهنا بنرجعها ل ket 0 to cancel the effect of the quantum register. فهنا الكوانتم اوراكل جنرال فورمات هنا حيعمل ابلكيشن بتاع الاكس جيت على كل كوانتم بت corresponding to 0 with the target qubit, ويعمل multiple control gate so that the minus sign will be applied, will be affected to the quantum base state that is marked. And then we do the X gates once more to flip back the quantum states. And here we can choose a certain target quantum state, get 0010 maybe. We do the number of qubits and we create a quantum circuit. We prepare the ancilla. The preparation of the ancilla is not included في الفانكشن بتاعنا المارك target state هنا, عشان بعدين حنستعملها في الجروبر overall Grover search algorithm, which is not practical to have the ancilla creation inside the function هنا. بس بنعمل preparation بتاع الأنسلة في الket minus state هنا X gate then the Hadamard gate, and then نعمل application بتاع the Hadamard gate على كل qubit which is main qubits, not the ancilla qubit. The ancilla qubit does not receive another Hadamard. It receives the main qubits receive the Hadamards to create the complete equal superposition that we are going to start with. And then we apply the mark target state to introduce هنا the minus sign in the marked elements or marked quantum base state. هنا the first qubit, as we said, is the quantum auxiliary qubit or quantum ancilla, or the ket y qubit that will apply the quantum phase, that will harness the quantum phase kickback عشان applying of the minus sign on the ket x register. بس هنا the application of the target state will invert the sign بتاع marked elements or marked quantum base states, and then بنعمل inverse بتاع the ancilla's setting from ket minus to ket 0 once more. And we can draw the quantum circuit, and we can display the exact quantum state resulting from this function. انتوا بتقدروا يعني تعملوا some other quantum state, maybe هنا 0, 0, 1, something like that, and you can check for yourselves. هنا نعمل application بتاع هنا يعني تعمل لك الفانكشن بتاعك بالضبط والكوانتم سيركت بتاعك بالضبط. فهنا عندنا 001. ففي الاوفرلاينج بتاع 001 في الكوانتم سيركت ما بنعملش 001. This is very important. بنعمل 001. And for every 0, we have an X gate that flips it to 1 so that the CNOT, the multiple control NOT operation, will be activated, and then we set it back to its original state. وهنا بنلاحظ the first qubit is always the ancillary qubit ولا the auxiliary qubit ولا the ket y qubit. وبنلاحظ هنا أنه ket minus appears when the ket x qubit is ket x quantum state is ket 001, which is equal to the target state being 001. And I invite you to do the same task, to do the same function, but with more target states or more controls right here. So, in general, as a in a nutshell, زي ما بيقولوا, the first step of the phase flip oracle. الاوراكل بتاعنا هتعمل application بتاع الفانكشن of f, هتاخد الفانكشن f وهتاخد الايكوال سوبربوزيشن بتاعنا, equal starting superposition هنا, وهتستعمل الفانكشن of f في الكادر ولا في الكونتكست بتاع الاوراكل اوراكولار بروجرامينج. هتستعمل الفانكشن f بتاعنا عشان تعمل الديتكشن بتاع الكوانتم ماركت بيس ستيت. هتعمل ابلكيشن بتاع الاوراكل على كل انتري ولا كل if you will quantum base state هنا، وهتعمل ديتكشن بتاع الكوانتم ماركت بيس ستيتس. اذا تعمل ديتكشن واذا كان تعمل ابلكيشن بتاع الاف تلقى اوتكم as one, so the minus sign will be appearing في الكت of x state which is the marked base state and it will be highlighted right here. بس هنا تقدر تسال انه هنا الكوانتم ستيت بتاعنا عندها ماينس ساين للماركت elements وعندها بلس ساين للانماركت elements. نقدر نقف هنا، نقدر ما نكملش يعني ما نكملش للاذر ستيبس. and this is a very important thing to understand لانه هنا صح we have minus signs for the cat for this example مثلا for the cat 010 cat 011 والcat 110 صح we have minus signs هنا، بس extraction of information from quantum circuits is not like this. احنا ما بنعملش extraction of information from quantum particles from quantum bits in general by this method. احنا بنعمل extraction of information from quantum states or from quantum circuits via measurements. والmeasurements are dependent of the amplitudes right here. So, for example, this particular quantum superposition is 3-qubit system, 3-qubit superposition. And if we do measurement, we can measure cat 001, for example, with a probability of 1 over 2 square root of 2 to the power of 2, of course, and it will be equal to the probability of measuring cat 010. So after measurement, after consecutive measurements, we build up probabilities, and we notice that the probabilities of cat 001 and cat 010, for example, are equal. فيعني من الميجرمنت we cannot distinguish them. We cannot distinguish cat 010 from cat 001. They are not distinguishable. Thus, we cannot know which is marked and which is unmarked. بس الستيب اللي بتعمل الديستنكشن دي is the amplitude amplification. The amplitude amplification starts from the fact that the measurement results are probabilistic. We do not get, for every measurement, we do not get the same result. Not like classical programs or classical algorithms. Classical algorithms يعطينا دايما نفس الاوتبوت ونفس الريزولت. بس quantum measurement, which is the extraction of classical information from quantum systems or quantum circuits, is not deterministic, is not constant. We can have a probabilistic result, a probabilistic distribution of results if we do multiple measurements, but the character of measurements pushes us to do a lot of measurements, a lot of consecutive measurements to get probability distribution. For example, if we have this particular system, وبنعمل a lot of measurements, a lot of consecutive measurements, we do if you write probabilities, where we do draw probabilities. هنلاحظ الدراونج ده، هنلاحظ state cat 000 observed with a number of times, which is equal to the number of observing of state cat 001, and so on and so forth. For each and every quantum based state في السوبربوزيشن هذه إذا كان نعملوا a lot of measurements, consecutive measurements, the number of times of observing cat 000 will be will be equal to that of cat 001, will be equal to that of cat 010, crucially, because this is a marked element, this is a non-marked element. And from consecutive measurements in this step, we cannot distinguish them. But we can use amplitude amplification. The name suggests what this step does. The amplitude amplification serves us to amplify and to increase correct states probabilities, well, marked quantum states probabilities, which is equivalent to saying we increase the amplitudes of marked quantum states and vice versa for the incorrect quantum base states. Amplitude amplification serves us by increasing the amplitude of the the amplitude of the marked quantum base state, which is equivalent to saying increasing the probability of measuring the marked quantum base states, and vice versa for the unmarked base states, which is the same, if you will, outcome that we observed right here. This is the inversion, and the query phase that was assured, that was given by the phase flip oracle that inverted the sign contained in the marked element, and the inversion phase will increase the probability of observing the marked element. Like here, we notice a sudden shift and a sudden increase in the marked element value. The same, if you will, impact or the same functionality is contained in the amplitude amplification process. Before we move on to this particular part, does anyone have a question about the previous part? Perfect. Okay. We can move on to the amplitude amplification part. In amplitude amplification, we are going to start with an equal superposition of all quantum-based states, like the oracle that we saw previously. The equal superposition can be visualized can be represented in this particular, if you will, plot diagram. And Ket Y right here, is the quantum-based state that is highlighted, that is, if you will, search, ولا that is marked. And CI here, هم الامplitudes corresponding to ket 00, ket 0000, ket 001, etc., etc. And this particular state of equal superposition can be offered by applying the Hadamard on each and every qubit present. The equal superposition that we talked about, which is 1 over the square root of n being the number of quantum-based states, sum of ket of I, and I being the possible n combinations of 0, 1. So this is the starting state of the amplitude amplification process. We apply a phase flip oracle of a certain target, ket Y. The phase flip will flip the sign of the oracle, of the, quantum-based state ket Y and move it right here. And بعدين بنعمل the diffusion operator that is corresponding to the step that we talked about, calculating the mean and then doing an inversion around the mean, so that this value for the unmarked elements, that is, this value becomes right here, the diffusion operator, inversion around the mean. You can see it as asymmetry alongside this line, asymmetry of the values contained in the plot, in the plots right here, alongside this red line, which is the mean of all values. Yani for the unmarked elements, these values will become right here, and for the marked element, which is thanks to the fuel phase flip oracle, it became right here, became under the reflection line, or under the mean of all values line. It will be amplified, it will be increased right here. This is the this corresponds to the first iteration that we talked about in the example في الbeginning في السession بتاعنا. And the result of the diffusion operator is an increase for the unmarked element, for the marked element, and a decrease for the unmarked elements for the first iteration. Because as we iterate, this might change. زي ما لاحظنا في beginning of our session. Now that we understood, this is the process of the amplitude amplification. Amplitude amplification هو process that is designed علشان نعمل increasing للamplitudes contained in the quantum-based states that are marked, that are searched, and to decrease the incorrect state amplitude, which is corresponds to saying that we decrease the incorrect state probabilities. And this is a process that will use the phase flip oracle, that will use the target ket Y, of course, but it will be a phase flip oracle that will flip the phase, and then with the diffusion operator, an inversion around the mean of all values, it will give us a new configuration that is faithful to what we want if we apply it in the first iteration. If we apply it in other iterations, it might change, and we will see how many iterations is optimal to get the most important and most, if you will, a most clear outcome. Sorry. Let's move on للإكسبريشن بتاع diffusion operator، لأنه هنا في كلمة operator، فيعني diffusion هنا diffusion action can be represented in a matrix format. والmatrix هنا is an operator, a quantum operator on a certain quantum state, quantum superposition that is. So الاكسبريشن بتاعنا we can inspire from the real number case. If we have a certain real number x هنا x1 x2 that so on and so forth, and we have the mean of all these values 1 over n times x1 plus x2 plus etc etc. Each and every value x will be inverted around the mean, so it will be moved right here. So we will be subtracting, or we'll be removing this particular distance twice from the initial value x. فيعني هنا x prime, which is the new value of x after the inversion around the mean, or after the diffusion operator right here, it will be equal to x, the old value, minus this distance twice. So it will be x minus 2 times x minus m, لأنه distance هذه is equal to x minus m. فيعني x minus 2 times x minus m, it will be equal to 2m minus x. 2 times the mean of all value, the average of all values, minus x. فهذه هي الاكسبريشن for real numbers. بس هنا احنا بنشتغل مع quantum states, quantum superposition, quantum systems. فهنا unitary operator will be analogous to the idea of real number expression. It will be d, which is the first letter in the diffusion operator. It will be d is equal to 2 times the outer product of state ket x, state ket s, sorry, minus the identity. And this operator, the outer product, is written in its matrix format, that is, right, like this. And this particular expression, if we, for example, يعني بنعمل لها multiplication مع vector معين x1, x2, etc., etc., this matrix will output 2 times 1 over n sum of xi for every x in this vector, and the resulting vector of the first matrix multiplication will be the same, 1 over n sum of xi, 1 over n sum of xi for each and every input, minus the identity. Of course, we'll be applying the same vector with a matrix multiplication with the identity right here, x1, x2, and so on and so forth. And for the new fuel vector, it will be 2 times the mean, which is this particular value, this particular summation, minus x1, 2 times the mean minus x2, 2 times the mean minus x3, which is exactly the format right here, but in the fuel, in the vector fuel representation, in the vector space. But yani, from our remark, the unitary operator right here, the outer product gives us the mean, and the identity gives us the same vector once more to get this particular value for each and every entry of our vector. And this state ket s, just a remark here, ket s is the result of applying the Hadamard on each and every quantum bit in the state ket 0. It is an equal superposition, which is offered by applying the Hadamard on ket 0 for each and every qubit in our quantum state. And it is 1 over square root of n summation of ket I, with I being the n bit combinations possible for n bits, that is. And this unitary operator, we can, if you will, see its action on a random quantum state ket psi. So ket psi here can be written as a linear combination between ket of s, the equal superposition that we talked about, and ket y, where the inner product between ket of s and ket y is equal to 0, which is equivalent to saying that the dot product between these two vectors, the corresponding vector representation, is equal to 0. That is saying that ket of y هنا, sorry, is anything but ket of s, the orthogonal subspace on ket of s right here. So ket of psi can be written as a linear combination between ket of s and ket of y, where these two vectors are orthogonal. And applying the diffusion operator on ket psi right here will give us 2 times this particular expression, which is the outer product multiplied by the vector, minus get psi, because we have an identity in the second part of our diffusion operator. And this particular inner product will give us A, because get psi is the summation between this vector in the vectorial representation. I'm not talking about, we're talking with quantum computing terms. This get psi here is a linear combination between a vector and another vector, which is orthogonal to the first vector. Sorry. So this inner product will be equal to the value contained in the vector, which is corresponding to ket of S. And this particular vector will have 0 from this particular inner product. So it will be discarded. That is. So this particular value will be equal to A. So we will be having 2A times ket of S, because this is still here, minus psi. We just replace psi with its expression. And then we will be getting A times ket of S minus B times ket of Y. What do we notice here? We started with a certain quantum state ket psi, which is the linear combination, as I said, between ket of S and the other vector orthogonal to ket of S, which is everything else between everything else but ket of S. And we are ended with the same vector, but with a minus sign right here. What do we notice? We notice the diffusion operator, if you will, inverts the coordinate corresponding to the vector or to the subspace orthogonal to ket of S. If you want to visualize it, this is ket W, the desired or the searched quantum base state, or the subspace of searched quantum base states for the case of multiple quantum base states. This is ket V, which is the other unsearched quantum base states. And this is S, ket of S, because ket of S is if you will, a superposition between all possible quantum base states, marked or unmarked. So it will be, if you will, in the middle between ket of V and ket of W, between the subspace of unmarked elements and the subspace of marked element. And the subspace of marked element, as we saw before, it can be one qubit, one quantum base state, or many quantum base states. And ket of S here is in the middle, but it is closer to ket of V because the number of unmarked elements is bigger than the number of marked elements. So the overlap between ket of S is bigger with ket of V, which is the subspace of unmarked elements, than the subspace of marked elements, ket W. And we notice that if we start with a certain quantum state, ket psi, which is a random quantum state, and we apply the diffusion operator, we notice that the coordinate corresponding to the ket S, or the overlap between ket psi and ket S, will not be changed from the, if you will, action that we saw here, but the coordinate corresponding to the, if you will, everything, the subspace that corresponds to everything else but ket of S, or the orthogonal vectors orthogonal vectors between them and ket S, which is corresponding roughly to this particular, if you will, quantum, if you will, subspace. The coordinate corresponding to this particular subspace will be inverted. They will acquire a minus sign, as we saw right here, ket Y, which is the subspace of the vectors orthogonal to ket S. So the diffusion operator will take us from this particular vector to this particular vector, D times ket psi. This is the visualization of the impact of the diffusion operator. And what do we notice here? We notice that we started with a certain quantum state, ket psi, right here, and we applied the diffusion operator, and the diffusion operator gave us a new quantum state that is closer to the subspace of marked elements ket W, which is equivalent to saying that we got closer to the marked subspace, which is equivalent also to saying that we increased the amplitudes of the, if you will, marked elements, which is something that we didn't do in the first step. The first step, the oracle that did the phase flip just highlighted the marked elements for the second step, which is the diffusion, yes, operator, which increased with the information of the minus sign that was acquired by the phase flip oracle. It increased the amplitudes corresponding to the marked elements with the diffusion operator, as we are seeing right here. So the diffusion operator will mirror, if you will, the input vector ket of psi over this quantum state ket of S, and it will increase the overlap with the subspace of marked quantum basis states in the case of being the first iteration, as we saw before. So if we increase the number of iterations, the third, the fourth, it might give us a different output, but it is for the first iteration. Right here, we are showing the visualization. And if we want to construct the diffusion operator D, let us first see this particular operator, which is 2 times the outer product between the ket 0 state, ket 0 tensor n, of course, because we are dealing with n qubit systems right here, minus the identity. It is similar to this particular, to the diffusion operator, but we have ket 0 as the quantum state, not ket s. So this particular operator, is a certain reflection or a certain, if you will, mirroring over the ket ket 0 tensor n, of course, subspace. So this will flip the phase of everything but ket 0 of tensor n, because here in our representation ket psi, the diffusion operator, which is the outer product of state ket s multiplied by 2 minus the identity, flip the amplitude or flip the coefficient of everything but ket of x, as we saw right here. And this is equivalent to saying that this operator will flip the phase of everything but ket 0 of tensor n state, because equivalent in an equivalent way, or in a consequent to the visualization or the action of the unitary operator, the diffusion operator on the ket psi state. And this equivalent to saying that we will be flipping the phase of only ket 0 tensor n state. Why? Because as we saw before, the phase, the global phase is relevant for our, if you will, quantum state. So here we know that this particular operator will flip the phase of everything but ket 0 of ket 0 tensor n. So if we have, for example, 0, 0, 0, plus 0, 0, 1, and so on and so forth, the application of this operator will take the plus and remove it to minus, and minus ket 0, 1, 0, and so on and so forth. And this is equal to minus a global minus right here, minus 0, 0, 0, plus 0, 0, 1, and plus 0, 1, 0, and so on and so forth. And we know that ket psi is a general quantum state, and minus ket psi are mathematically different, right? Yeah, but from a physical point of view, they are not different, because if we do consecutive measurement on psi and minus ket psi, we get the same probabilities for each and every quantum basis state contained in ket psi and ket minus ket psi. Sorry. So if you will have these two, if you will, quantum states, they are regarded, or they are considered as identical from a physical point of view. So these two quantum states are identical. Thus, the application of this particular operator will only flip the phase contained in the ket 0 tensor n state, which is equivalent to saying that this operator, this particular quantum state, is equivalent to this particular quantum state, because they have only a global phase right here. And this is exactly the action of the phase flip oracle. If you noticed, here we have a certain operator, and this operator only flips the phase of ket 0 tensor n state, quantum state, that is. And this is exactly the functioning of a phase flip oracle with a target state ket 0 tensor n quantum basis state. Okay. So, يعني, this is exactly the functioning of the phase flip oracle. And from what you might notice, this particular quantum state, which is the diffusion operator, diffusion operator, yeah, is equal to the Hadamard tensor n multiplied by this particular operator that we discussed, multiplied by another Hadamard tensor n, because the get zero tensor n multiplied by undergoing a certain Hadamard operator tensor n, that is, will give us kit of s, and likewise for the bra notation, or the inverse of our vector. So this particular operator, which is the diffusion operator, is actually the Hadamard operators applied on each and every qubit. The Hadamard operator applied on each and every qubit, followed by this particular operator, which is really a phase flip oracle with a quantum target, quantum base state, kit 0 of tensor n, followed by another Hadamard applied on each and every qubit, qubit of our n qubit system. So here we understood how the second phase helps us acquire the information from the first phase, or the first step, and apply the diffusion operator, or apply the amplitude amplification to increase or amplify the amplitudes or the probabilities of observing the marked quantum states. And in general, if you understand better what the amplitude amplification is constructed of, really, the amplitude amplification is constructed of the phase flip step, the phase flip that highlights the marked element with a minus sign, and then it relies on the diffusion operator to use the outcome of the phase flip oracle to create a amplified amplitude corresponding to the marked element. And in this way, if we do a certain measurement in this step, we will notice that, for example, if we have the state 010, for example, is the target state, we will notice that get 00, for example, that is, we do 1,000 shots or 1,000 repetitions of our measurements. We notice that 000, for example, is measured 170 times. 001 is measured 168 maybe times, but 010 will be measured, in this case, where 010 is the target state, will be measured maybe 500 times or something like that. So the if you will, distinction between the number of measurements between the marked and unmarked elements will be visible, a little bit visible, but we will be repeating this, if you will, amplification process to construct the actual Grover search algorithm, so that these number of repetitions will be as minimal and as distinctive, and as, if you will, visible, the difference between them will be as visible as possible. Like the first example that we introduced, we can stop after the first iteration, but it is not an optimal, if you will, configuration. We can apply more iterations with a certain number of iterations to be detailed later, to get an optimal, if you will, number of repetitions. And to apply the diffusion operator, we know how to apply the oracle, like we talked before, but to apply the diffusion operator, we first apply the Hadamard on each and every qubit, then we apply this particular operator, which is equivalent to a phase flip oracle, with the target state with the target quantum base state get 0 tensor n, and then we apply another layer, if you will, of Hadamard operators. Let's now see the amplitude amplification process before us. We can start with two, if you will, classic quantum registers for our two quantum states. We start the classical register to contain information, and then we initialize our, if you will, quantum registers. We start with a Hadamard for each and every, if you will, quantum knot and Sela qubit main quantum states, and we apply the, if you will, the X gate and then the Hadamard gate on the ancilla qubit to create the Ket minus state, and we create a barrier to better visualization. So this is, if you will, the introduction, or sorry, the initialization for our step of the phase flip oracle, and this is actually equivalent to this particular step. We created an equal superposition of all main quantum-based states, and for the auxiliary quantum state, or for the ancillary quantum state, we created it in the state of Ket minus. And now that we created this particular initiation of our algorithm, we are going to create the phase flip oracle, and the phase flip oracle here will be appropriate, or will be directed to the quantum state Ket 0, 1, 0. This is the marked element right here. So we need to, if you will, apply the X gate in here and in here, 0, 1, 0. So you need to apply the X gate right here and right here, like we talked before, so that from this particular superposition, the quantum state Ket 0, 1, 0 will be transformed to 1, 1, 1 under the impact of the two X gates, and the multi-control node operator will be activated, and then we apply another time the X gates right here to cancel the effect of these initial quantum gates, and to feed the result of the phase flip oracle to the diffusion operator. And the diffusion operator right here, this is the code for the oracle, and this is the diffusion operator right here. Sorry. The diffusion operator right here will begin with a layer of the Hadamard operators, like we talked before, and then if you will, an oracle that flips the quantum-based state Ket 0, 0, 0. And flipping the quantum-based state Ket 0, 0, 0 is actually exactly applying the X gates for each and every entry of the main quantum register, so that the quantum state Ket 0, 0, 0 will be transformed to 1, 1, 1, and it will be flipped. So this is a very important, if you will, step to understand here. The oracle that flips the sign of the quantum-based state Ket 0, 0, 0 is actually three X gates for the main quantum entries of our quantum register, and an ancillary qubit as target of a 3-qubit control, or 3-control qubit gate, where the main quantum bits or quantum register is the control of this particular multi-control quantum gates. And then we do another wave of X gates and another wave of Hadamard gates to cancel the impact of these two layers. And then we move on to measurement. And as we talked before, after one, if you will, iteration of our amplitude amplification process, we do a lot of measurements, a lot of consecutive measurements, and this is done by the backend offered by Qiskit, the IBM library. It will do some simultaneous consecutive measurements, 1,024 shots to be exact, and it will give us, like we predicted, Ket 010, or the outcome 010, the targeted outcome right here, which is measured a lot of times. And from the executor point of view of the algorithm, up until this point, he didn't see the oracle in and of itself. The oracle right here is a black box, and he didn't know anything about the marked elements. But from these consecutive measurements, he can understand, okay, Ket 010, from one iteration, he can understand, okay, Ket 010 is the marked element. But we can repeat the amplitude amplification process another time to get better results, like the example that we introduced in the beginning of our session. And if we introduce it twice, so here we do an oracle that if you will, highlights and introduces a phase flip for the quantum-based state Ket 010, and then a diffusion operator, and then the same oracle once more, and then the same diffusion operator once more. We do consecutive measurements with the same simulator, and we get even better results. Here, the non-search elements are, if you will, approximately not seen at all, but only the marked element or only the search element is seen in a, if you will, very big probability of observance. We can also repeat the amplitude amplification 3 times, like here, right here, like we are seeing right now. The same oracle and the same diffusion operator repeat 3 times, and we get bad results like we predicted. And for a general format or a general representation of the amplitude amplification, we can do it like we did with the phase flip oracle. Can create a general function for the diffusion operator, and we can introduce this particular operator in an example right here with the quantum-based state as a token state ket 010. We can use the mark target state, the first function that we defined, and the diffusion operator, the second function that we defined, and we do certain, if you will, one iteration of our amplitude amplification process, and we get these results, which are not optimal, but if we do another iteration, it will get better. And the same task is repeated here. Can you do the same function? This function here, the diffusion operator, does the diffusion for the case of one target qubit, but can you do the same task for many quantum base states? Now that we introduced the main components of the Grover search algorithm, let us introduce the algorithm in its entirety. Okay, before we move on to the Grover search algorithm, does anyone have a question? Okay. We can move on to the overall definition of the Grover search algorithm. As we talked before, the Grover search algorithm will be executing a certain search through a list for a defined item, for a particular item, and this list is unordered. Classical approaches say that if our list is sorted, ordered, alphabetical order or numerical order or something like that, we can use binary search, a certain technique of search in a list, and it will, if you will, take a complexity of big O log 2 of n. And if our list is unsorted, classically, we don't have anything to do, really. We just have to brute force it, and we will be ending up with a complexity of big O of n, with n being the number of entries of our list. And our list, and it can be number of entries of our, if you will, search possibilities or something like that. But for the Grover algorithm, the quantum counterpart for our search algorithms, the Grover algorithm will execute the same task of searching through a unordered list or unordered, if you will, group of possibilities with a better complexity. And the Grover search algorithm works as such. It will have a layer of Hadamard's, as we talked before, to create equal superposition, a superposition between all possible quantum base states with equal, if you will, amplitudes for each and every quantum base state. And then we'll be having after this step the quantum state ket S, which is the summation of each and every quantum base state divided by the number of entries, square root of number of entries in our list. And then we'll be moving on to the core of the Grover search algorithm. The first step is the phase flip oracle. The phase flip oracle that will introduce the minus sign for the marked quantum base state or marked quantum base states eventually, like we talked about before. And this minus sign will help the diffusion operator to exert or to do its inversion around the mean and amplify the amplitudes or the probabilities associated with the marked quantum base states. And then we repeat this process n times, in a certain number of times, and there is an optimal number of times to be defined right now. And then we do consecutive measurements of our circuit to build up probabilities and statistics like we talked before, and to, from these statistics, to derive or to know really the, if you will, the marked element at hand. Okay, now that we have, if you will, our part of the Grover search algorithm, we can represent it visually, the whole algorithm. We can have this particular subspace which is the constructed of the quantum base states which are marked, one quantum base state which is marked, or many quantum base states which are marked, which collectively will be represented as Kit W, and Kit V, which is the subspace of unmarked quantum base states. We start with the quantum state Kit S, as this particular step suggests. We start with the Kit S quantum base state, and then we apply the phase flip oracle. Okay, the phase flip oracle, and this particular phase flip oracle will move the Kit S to U Kit S, which is the second step, the result of the phase flip oracle. It will flip the coordinate of Kit of S corresponding to the marked element subspace. And from this particular, if you will, second step, we will be applying the diffusion operator, the D times U times Kit of S, which means that we're applying the diffusion after the phase flip oracle. And the phase flip oracle right here, and the diffusion operator, right here, will move us closer to the marked subspace of elements. And here we notice that the overlap with Kit W increase and the overlap with Kit V decreases. And if we repeat the process once more, we take this particular step and we apply the phase flip oracle once more, it will take us further down this particular direction. And the diffusion operator will take us even more closer to the marked subspace of elements. We kind of visualize it right here. Here, the starting point, Kit S, here will be the equal superposition of all quantum base states. It will move us down to this particular quantum base state, which is quantum state, which is the result of the phase flip oracle, and then it will move us up through the diffusion, or with the diffusion operator, to this particular quantum state, which is the result of applying the diffusion operator one time. And then this is the result of applying the oracle and then the diffusion one more time, which is equivalent to saying we applied the amplitude amplification process one more time, and it got us closer to Kit W, as we see before, as we see here, sorry. And if you notice here, this is the starting point, Kit of S. It will take us this particular quantum state, and this is the angle theta. Taking this particular quantum state, Kit of S, to this particular quantum state means that we are going to do two rotations. One rotation and then another rotation with an angle theta. And if you will take in this particular quantum state to this particular quantum state, is equivalent to saying that we are doing another two set of rotations. This particular first rotation, taking this vector, this particular vector to here, is equivalent to saying that we took this vector once and then twice with the same angle, which is 2 theta. Thus, this particular angle, the total angle between this vector and the Kit V vector, or the x axis, will be 2 theta plus theta. Thus, the first iteration will take Kit of S from theta to 3 theta. And if we repeat the process of amplitude amplification once more, it will take us from 3 theta to 5 theta. And this is really the pattern here. For the 0th iteration, we have theta. For the first iteration, the first iteration of the amplitude amplification process, we have 3 theta. For the second iteration of the amplitude amplification process, we have 5 theta, and so on and so forth. For n iterations, we have an angle of 2n plus 1 theta. But we want 2n plus 1 theta as close to pi over 2 as possible. Why is that? We want to get closer and closer, and we want to get the closest possible, to Kit W, or the marked subspace of elements. Thus, this particular angle, we want to approach it, or want to increase it, we want to approach it to pi over 2 as much as possible. And we know that theta is equal to 1 over square root of n. Here, theta, because of the sine laws, theta is really this particular value divided by the hypotenuse, and we know that the hypotenuse is equal to 1 because this is a valid quantum state. Thus, the length of the vector of the quantum state is equal to 1. Thus, theta will be equal, sine theta will be equal to this particular value, which is 1 over square root of n, the overlap between Kit of S and the marked subspace, if the marked subspace has just one value. And Sin of theta, as we said, will be equal to 1 over square root of n, which is the overlap or the amplitude of the one qubit, overlap between k of s and the one quantum basis state marked subspace. And from Taylor approximations, we approximate that theta will be equal to 1 over square root of n because if you will, n will be or might be, if you will, very large, so that we resort to Taylor approximations. So we notice that if n is very, very big, the number of iterations, the number of optimal iterations, so that the angle at hand will be closest to pi over 2, will be equal to pi over 4 times square root of n. And this in the case of one quantum basis state that is marked. If you have 2, 3, and so on and so forth, quantum basis states that are marked, we will be, if you were changing the value of the sign right here, or say changing the value of the sign right here, and the overlap between k of s and the marked subspace from square root of n to square root of n over k, and k will be the number of search elements. This is n, sorry, and square root of n over k will be the number of marked elements at hand. And we notice from here that we are going to repeat our, if you will, amplitude amplification process this particular number of times, which is pi over 4 times square root of n for the case of one marked element at hand. So we notice that we are going to repeat this process in a number which is if you will, equal to big O of square root of n complexity, because we are going to repeat pi over 4 times square root of n, which is a scalar times square root of n, which is a number of a complexity of big O square root of n. Thus, we notice that our Grover search algorithm with a number which is a multiple of square root of n, which is a complexity of big O square root of n, with such a complexity will, if you will, do the task that was required to be of a complexity big O of n for classical approaches. Thus, the Grover search algorithm, it is the first algorithm that we are seeing that we are seeing together right now, which has a clear advantage over classical approaches in real-world important, if you will, applications. And this is all thanks to the principles of oracular programming and oracular, if you will, design, and the principles of phase kickback and the principles afterwards of the diffusion operator and the diffusion principles based on the phase flip oracle. Now, let us move on to the part of the Grover algorithm definition right here. We are trying to, if you will, put all the pieces of the puzzle together right here. We are defining a target quantum state 001 right here, and we are going to define n, which is 2 times of number of qubits, which is the possible quantum base state or the possible solutions of our quantum search, and big M will be equal to 1, which is the number of solutions. For this particular cell, we'll be working with just one marked element, and you will be having an exercise, the same exercise, which is trying to, if you will, extend this particular quantum Grover search algorithm for many marked element search. So create our quantum circuit. We do our initialization, like we talked before right here, with the pair of Hadamards, and we create the ket minus for our ancillary qubit. We do our baryon to separate our initialization of our circuit from the rest of the parts of the Grover search algorithm. This is the part of the initialization. The main qubits will be subject to just a Hadamard, and for our ancillary qubit, it will be subject to the X gate, then the Hadamard gate. And then we move on to applying the Grover iterations. The Grover iterations, which are, if you will, consecutive iterations or consecutive repetitions of the amplitude amplification process, which is phase flip oracle, then diffusion operator consecutively. So this is the phase flip oracle, and the phase flip oracle works so that it flips the sign of the quantum basis state Kit 001, which is the, if you will, target state at hand, this right here. And then after the phase flip oracle, we move on to the diffusion operator, starting with the Hadamard gates, and then the phase flip oracle, but for the Kit 00 state, 000 states, sorry. So it will be all X gates right here, and then the multiple control node operator, and then the inverse of the application of the Hadamard and the X gates right here to cancel the effect of this particular first two layers. And then we repeat the phase flip oracle and the diffusion operator. And then we, if you will, do our measurements on the main qubits, and the ancillary qubit will receive Hadamard and then X gate once more to cancel the effect of transforming it from Kit 0 to Kit plus. And we will be repeating this particular amplification two consecutive times, that is, which is given by the formula that we saw before right here, pi over 4 times square root of. Okay, now we'll be applying the simulator, and we are going to, if you will, measure a lot of times to 1024 consecutive times, and we notice that after the optimal number of iterations, we have an optimal result with Kit 001 observed a lot of the times, mostly observed Kit 001, and for the other values to be observed, to not be observed at all. And this is the exercise that we talked about. You might want to try and adjust this particular reasoning or this particular, if you will, cell, but for the case of multi-target states, a lot of target quantum states, you can try it with the functions that were predefined earlier when your quantum in your coding cells, and you can use it to extend our search to many target quantum states. And just a little overview about the global search algorithm. The global search algorithm is a very important algorithm. A lot of applications in quantum programming, quantum technologies in general. For example, the most, if you will, basic or the most intuitive application of the global search algorithm is the plain or the usual searching task of searching for a certain element or a certain, if you will, particular solution from a lot of possible solutions, or the possible elements of a certain list or a certain database in general. You can apply it also in the context of combinatorial optimization, like the example that we saw before right here with the traveling salesman problem. You can use it in context of a certain, if you will, search between a lot of possible solutions, a lot of possible combinations of solutions. The global search algorithm can prove helpful in finding the correct solution or correct solutions. It can also be used in applications in cryptography and post-quantum cryptography, where key prediction or key, if you will, decryption can be extremely, if you will, extremely accelerated with global search algorithm. And finally, it can be used in the context of machine learning, quantum machine learning, etc., for some tasks of going through a certain database or something like that to conduct a search or an optimized quantum search for a certain quantum machine learning or machine learning context in general. So this is a very important, a very, if you will, influential algorithm, and it likely will encounter you if you desire or you decide to continue your quantum journey. And that's it. For today, this is our session. We learned how can we formulate oracles. We learned how can we formulate especially the phase flip oracles, and then we learned how can we formulate the diffusion operator and combine them together in consecutive iterations to create meaningful algorithms. So, does anyone have a question about this part? Okay, I believe no one has a question.
اعتقد السيشن كانت ممتازه جدا يا محمد يعني.
ماشي مشكلة. ومتأسف علشان أنا دورت في اللغة بالإنجليش عشان المصرية بتاعتي I don't think it's understandable.
لا لا لا، ده ممتاز جدا، لا عادي، مش
أوكي
مشكله.
أوكي متشكر.
ماشي.